Hello everyone, good evening. This summer I did my summer internship under Professor Amresh Shivaji on the topic of theoretical high-energy physics. So basically my work revolved around calculating the integral, one loop integral for the general 3-point function and a special case where one of the external legs is massless. So there are basically two ways by which we can calculate these integrals, either by numerical methods or analytically. So I did all my calculation analytically, and it would be very cumbersome to show all those calculations and would not lead to any meaningful results. So what I'll do, I'll use those results simplified and try to explain the physics as much as I can with those results and see what implications we lead to. So basically we'll first start with how the quantum field theory arises. So basically in 1925, Heisenberg came with his uncertainty principle and his Schrodinger's wave equation. The Schrodinger's wave equation was non-deterministic in nature and had only a single particle solution. So Dirac later proposed his famous Dirac equation where he combined the special relativity and quantum mechanics. But it still poses a problem of negative energy solution, which was the same case for the Klein-Gordon equation. So later, Dirac proposed his Dirac-Coulomb theory, where he says that there is an infinite sea of electrons, negative energy sea of electrons, and any excitation in this negative infinite energy sea will lead to a creation of an electron, and the hole that we have will be an antiparticle or a positron. But this interpretation was very ad hoc and was not very intuitive in nature, so a better formalism was later stated with the introduction of quantum electrodynamics and quantum field theory. So here, instead of quantizing our position and momentum, we are going to quantize our fields, and which later automatically leads to a creation and annihilator, and we'll see how the QED Lagrangian leads to perturbation theory. So in the initial stages of QED, we see there were divergences which need to be resolved, showing the Tomonaga, Taiman, and Dyson, they all combined, and they introduce a method to normalize these divergences, which leads to some meaningful results which we could measure. A physical observable in this case, maybe a cross section or a decay rate or anything else. So the general framework of QFT, based on what fundamental force we are considering for electromagnetic QCD, for strong interaction QCD, and for the electro-weak theory for the weak plus the electromagnetic force. So this is my Lagrangian for the QED. Here you can see it has three terms which we can separate out. The first term corresponds to a free fermion. The second term of free photon, and this third term is the interaction term, which basically gives rise to all the interesting physics that we see. This interaction term will lead to creation of new particles. So we see there is a coupling between the equation. When we solve the Euler-Lagrange equation, we see that for the Dirac equation, there is an A term which comes from the photon, and for the Maxwell equation, there is a J mu, which is the current density term, which comes from the fermions. So there is a coupling between the two equations, and there is no implicit way to solve this equation exactly. So this even motivates more to use the perturbation theory. I'll just give you a brief idea of how we connect this to our Feynman diagram. The maths is very large, so we will focus on the results that we have. So this is our S matrix. This is my basically time operator of how the states evolve, e raised to power minus IHT, where H is for my overall H interaction. So this S matrix basically defines the transition probability of my state going from I to F state. So when we solve this, this is the expression that we get. The first term corresponds to the same I and F. For example, electron just going to electron and there is no interaction. So the S matrix is just one. The second term is the interesting term, where we see we have cross terms, and these are the interaction terms that we see. The 4 delta function is just for the conservation of force momentum. this is my interaction Hamiltonian. There are ways to solve this. Would be given in any high energy course book. So we'll just see the steps we follow. We perform Wick's, we use Wick's theorem, we open the Dyson series, and now the Dyson series, we can club those solutions, and that's what Feynman did. Feynman basically used his Feynman rules, and he was able to show these integrals a form of his Feynman diagrams with his Feynman rules. So it acts as his bookkeeping devices. So instead of writing the whole Dyson series and the integrals, we'll be able to write all those in just the Feynman diagrams. So these are his Feynman rules for all the propagators, the external leg, internal leg for muon photons. So according to this, we can convert our Dyson series to our loop diagram or any Feynman diagram. So we see now we have the QED Lagrangian. We got the diagrams. The diagrams are directly in relation with our capital M, which we got from the S matrix, and its square will give you an observable differential cross section. So here we can justify or basically testify our theory if all this is leading to some physical interpretation which we can measure. And all these observables are directly associated with the S matrix, which are indeed associated to the M and plus the Feynman diagrams. So we use high energy physics basically to go things at shorter distance. We have E is equals to xc by lambda. So higher energy will have a smaller lambda. So we can go things at a smaller scale. So greater the energy, the more chances we will see of finding a new particle. So these new particles will have some contribution in our loop diagrams. We'll see further. And these corrections is basically deviate from our original theory, and we can thus predict there might be some new particle which still need to be discovered. So these are the two Feynman diagrams at core. One is a tree-level diagram. There is no internal propagator there. Just the P initial coming and P outgoing. There is no internal propagator momentum here, and we can exactly solve this. And for this is the case of a one loop diagram. So here we have an internal momentum of L, and this L can vary anywhere from 0 to infinity. There is no restriction on that. So basically, these are the things that give rises to infinities in our Feynman diagram, which we will see. So this is a general form. So this is the general form of our endpoint scalar function, Feynman diagram. We see this L can vary anywhere from 0 to infinity, and note this integral in my Minkowski space-time. So I need to convert it into Euclidean space so that I can further solve this. This was an example of a two-point function, the Bubble integral that I showed in this diagram. And now we'll focus our shift to the simplest possible case, the one-point function for the tadpole. This is the simplest case. We just want to see how beautifully those infinities arise and how we are able to separate them and reduce them to a form where we can use it to find an observable. So here we have our tadpole integral. We see for let's say for a large momentum case, we see the denominator m square term is very small, so we have 1 upon L square in our denominator. This is Minkowski space-time. We do bit rotation and convert this to Euclidean space. Now Euclidean space we can easily transform it to spherical coordinates, and this is the spherical coordinates conversion after this. The spherical part coordinates goes outside, and this is the radial part that is left. So the integrand looks like this. Now we have dimension d is equals to 4, 3 for the space and 1 for the time. And if we put d equal to 4 in our calculation, we get an integrand of L, and when we integrate it, we get a lambda L square term. And this term goes to infinities for large L. So these are the divergences that we see. Now to tackle this divergences, we need to regularize our integral. There are many ways to do it. The first proposed way was this. We just define a cutoff for our momentum, like a highest point where it can reach above it is out of our domain. So we perform this integral. I have just written the integral that we get after doing all that. So this is the integral we get. You see there is a direct lambda square quadratic term here, and also the IISER term also consists, also contains a lambda here. So we see there are quadratic divergences and we are not able to separate any divergences from here. We will also see why this method is not very good. So the second way was the dimensional regularization. This is a trick which is mostly used when we solve any of the Feynman loop diagram. We introduce d equal to 4 minus 2 epsilon, when epsilon tending to 0 farad, d is equal to 4 k. We introduce a mu which is which sir?
Is it IISER Mohali?
Yes. No, they are not the same. No, they are not the same, sir. They are not the same. Those are just for the poles. The LIs on my real axis, I just want to shift them on the imaginary poles. So they are not the same. So we define that parameter as going to 0. This is not going to 0. So this I write as my normalization constant, renormalization constant to match my initial mass dimension, which was initially the case. So over one dimension becomes consistent. And now when we solve this, we see 1 upon epsilon pole comes outside. So there is no other pole here. So we are able to isolate my divergence, and now we see why this method of dimensional regularization is even better, because it preserves the Lorentz invariance and gauge symmetry. Because in cutoff, we are defining our momentum to have some particular threshold. So if we change our frame, we might go outside that cutoff, which will break the gauge, and thus the QED, which has charge conservation, will not hold. So a better way to regularize is to use the dimensional regularization. So in all of QFT we use dimensional regularization. So now after regularization we have that 1 upon infinity, 1 upon epsilon term which goes to infinity. This is basically the UV divergence because we defined it for large and tending to infinity case. So now we need to renormalize our theories, we need to absorb those infinities. So we use some bare parameters. These parameters are not observable. The observable ones are the left that are left behind after subtracting those infinities from. So subtracting those infinities do not lead to any change in physical observable. Now, this was the whole part that we did. I did for the three-point function. So I want to show one example. Of how we use this correction. Basically, how Schrodinger uses correction to show the change in magnetic moment for the spin-half particle. So this is my normal magnetic moment, and my Dirac equation predicted my G factor to be 2, and the quantum loop shift this G factor by this, where A is my anomalous magnetic moment. So after this is my diagram. An electron going, interacting with a photon, and an electron going out. It could be any electron. The first order of correction does not depend on what electron you are choosing, be it tau on muon or an electron. It is independent. That alpha is the fine structure constant. So when we solve this, the first order correction is independent of what fermion we are using, what electron we are using. So the second order correction, the higher loop diagrams, leads to a greater correction when we use a muon, because the second order correction is directly proportional to mass square. So muon we know has 200 times more mass almost. So there would be greater correction in our energy level, and thus we see a better correction in our perturbation theory. Like for the case of electron, it's almost negligible. So here we have combined. This is the standard model prediction, the whole aim that we predicted. These has the QED loops, the electroweak loops, and the hadronic loop. We have only considered the QED loops as for now. There could be other loops as well with other fundamental forces that are involved. And these were the experimental results. So we see it is close, it is not that close yet. So that's the discrepancy. The difference is 4.2 sigma almost. So this leads to new theories that there may be some new particles that we have still not discovered because their contribution will be there in the loop diagram. So there may be something left.
questions, if any? Okay, then we can move on.